Welcome to our latest video on the topic of redox titrations. This is the second video in the series and is suitable for A-level students. By the end of this video lesson, you should be able to write iron electron half equations for the reduction of common oxidizing agents such as MnO41- and Cr2O72- and be able to combine these with half equations representing oxidation of species such as iron 2. You should also be able to use data from redox titrations to find the concentration, mass and percentage mass of substances. Now, in our previous video on redox titrations, we learnt that a redox titration is one which involves both reduction and oxidation reactions, and three common redox techniques involve the manganate 7 ion, MnO41-, the dichromate 6 ion, which is Cr2O72-, and the fire sulfate ion, S2O32-. And in our last video we learnt that the manganate 7 ion and the dichromate 6 ion are oxidizing agents and the fire sulfate ion is a reducing agent, and redox titrations can be used to determine the purity of samples. For example, they're regularly used to analyze metals and their compounds, and in this video we're going to look at how we use redox titrations to find the concentration of a reducing agent and also the mass and percentage mass. Now, when oxidizing agents such as the manganate 7 ion and the dichromate ion oxidize substances, they are themselves reduced. And in our previous video we learned how to write a half equation to show the reduction of these oxidizing agents. In addition, we learned how to write half equations to represent oxidation reactions and how to combine these half equations that represent the reduction and oxidation processes that are taking place in a redox titration. Now, in our last video we attempted a number of titration calculations where we had to use these overall equations that we'd produced by combining the half equations for reduction and oxidation processes. Now, to test your understanding of this, we have a series of practice questions here. Here's the first practice question. Read through the question, pause the video, have a go at parts A and B, and then we'll go through the answers. So in this first question it says, in a redox titration, 24.30 centimeters cubed of potassium manganate 7 solution at a concentration of 0.0200 moles per decimeter cubed was required to oxidize completely 20.0 centimeters cubed of acidified iron 2 solution. And the first part of the question is asking you to use the following iron electron half equations to construct an overall equation for the manganate 7 ion oxidizing the iron 2 ion, and it's a 1-mark question. So to combine two half equations you have to have the same number of electrons in each half equation. Now, we have 5 electrons in the top half equation and 1 electron in the bottom one. So I have to times the bottom equation by 5. Now, when I then add these two equations together, the electrons will cancel out. So the overall equation is MnO41- plus 8H plus 5Fe2 forms Mn2 plus 4H2O plus 5Fe3 . And if you had that correct, you get 1 mark. So part B says calculate the concentration of the iron 2 ion, and it's a 2-mark question. Now, if we look at the question, we know the volume of potassium manganate 7 solution needed to oxidize the iron 2, and we know the concentration. So as we know the volume and concentration of the manganate 7 ion, we can work out the number of moles needed to oxidize the iron 2 solution. So all we do is concentration over 1,000 times volume, so it's 0.0200 over 1,000 times the volume, which is 24.30, and if you do that you get the following number of moles. It comes out to be 4.86 times 10 to the minus 4, and that's the moles of MnO41-. Now, to work out the moles of iron 2, you just use the equation that we've produced in part A. And you do this because you need to know the ratio of manganate 7 to Fe2+. And you can see it's a 1 to 5 ratio. So all I need to do to work out the moles of Fe2+ is multiply the moles of MnO4- by 5. And if you do this, you get a value of 2.43 times 10 to the minus 3. So that's the moles of Fe2+. Now to work out the concentration is equal to moles times 1,000 over volume. So the moles is 2.43 times 10 to the minus 3. You times it by 1,000 and you divide it by the volume of Fe2+, and the volume of Fe2+ is 20.0. So it would be 2.43 times 10 to the minus 3 times 1,000 over 20, and that will give you a concentration equal to 0.122 moles per decimeter cubed. Now if you had the correct moles of Fe2+, you get 1 mark, and if you had the concentration correct, you get the full 2 marks. So here's our second practice question. Once again, read through the question, pause the video, have a go at parts A and B, and then we'll go through the answers. So question 2 says potassium dichromate is an oxidizing agent in acidic conditions. During a redox titration, the dichromate ion is reduced according to the following equation. And then part A says write an overall equation to describe the reaction of potassium dichromate with Fe2+ ions. And part B says to calculate the mass in grams of iron 2 sulfate crystals, which can be completely oxidized in acidic solution by 25 centimeters cubed of aqueous potassium dichromate of concentration 0.0300 moles per decimeter cubed. So to write the overall equation, we have to first write the half equation for the oxidation of Fe2+ ions. So the half equation would be Fe2+ goes to Fe3+ plus an electron. And then to write the overall equation, we combine the two half equations here. And to do this, we need the same number of electrons in both equations. So we need to times the bottom equation by 6, because we need 6 electrons in both equations. And then when we add these two half equations together, we get the following overall equation. It would be Cr2O72- plus 14H plus 6 Fe2+ goes to 2Cr3 plus 7H2O plus 6 Fe3 plus. And if you had this whole equation correct, this overall equation, you get 1 mark. Now when combining the two half equations, the electrons just simply cancel out. This is because we've got plus 6 electrons on the left hand side of the first half equation and plus 6 electrons on the right hand side of the second half equation. So when we combine these half equations by just simply adding them together, the electrons cancel out, and that's why the electrons do not appear in the overall equation. So for part B, we have to work out the mass in grams of iron 2 sulfate. So we've got the concentration of potassium dichromate here and the volume. So the first thing we need to do is work out the moles of dichromate, and we do this by using the following equation: concentration over 1,000 times volume, and the concentration is 0.0300. We divide this by 1,000 and we times it by 25, and that will give us the moles of dichromate. Now the moles of dichromate is equal to 7.5 times 10 to the minus 4. Now we know the moles of dichromate, we can use this to work out the moles of Fe2+, because all we need to do is use the equation, and the overall equation tells us that the dichromate and Fe2+ are in a 1 to 6 ratio. So to work out the moles of Fe2+, I just times the moles of Cr2O72- by 6. So it's 6 times 7.5 times 10 to the minus 4, which equals 4.5 times 10 to the minus 3. Now that I know the moles of Fe2+, I can work out the mass of the iron 2 sulfate crystals, because the iron 2 sulfate crystals has an MR of 278. So I know the moles, I know the MR, and mass is equal to moles times the MR. So if I do 4.5 times 10 to the minus 3, and I times it by the MR, which is given to me in the question, 278, I can find that the mass of iron 2 sulfate crystals is equal to 1.251 grams. Now this is a 3-mark question. If you got the correct value for the moles of dichromate, you get 1 mark. If you had the correct value for the moles of Fe2+, you get 1 mark. And you get the final mark for getting the mass of iron 2 sulfate correct. Now at A level, a common experiment carried out involves using a redox titration to find out the percentage mass of iron in an iron tablet. Now, iron tablets contain iron 2 sulfate, which is a soluble, inexpensive form of iron supplement. And to work out the percentage of iron in an iron tablet, you use the following method. A chemist will accurately weigh samples of the tablet and dissolve these in sulfuric acid, and then titrate samples of this solution with an oxidizing agent such as potassium manganate 7. Now the titer values can be used to work out the moles of potassium manganate 7, and by using the overall ionic equation you can work out the moles of Fe2+ in the conical flask. Now once you know the moles of Fe2+ in your conical flask, you can work out the moles of Fe2+ in the original solution. And if you multiply this by the AR value of iron, 55.8, you can work out the mass of iron in grams. Now to work out the percentage mass of iron in an iron tablet, you need to know the mass of the iron tablet. And if you've worked out the mass of iron in grams in your sample, and you know the mass of the original iron tablet, you can calculate the percentage mass of iron in the tablet. Now if you attempt past paper questions on redox titrations, you will very often see past paper questions that involve you using data from experiments such as these to calculate the percentage mass of a metal. Now past paper questions will often ask you to calculate the percentage of iron present in an iron tablet, or they'll ask you to calculate the percentage of iron present in an iron nail or sample of steel. So now we're going to give you some practice at these sorts of questions. So here's the first practice question. Now this comes in 4 parts, parts A, B, C and D, and parts A and B are on this slide. So we want you to read through the question, have a go at parts A and B, and then we'll go through the answers, and then we'll have a look at parts C and D. So now let's go through parts A and B of this first practice question. So question 1 says a 4-gram sample of powdered iron tablets containing hydrated iron 2 sulfate was dissolved in some dilute sulfuric acid and the solution made up to 250 centimeters cubed. A 25 centimeters cubed sample of this solution was titrated with 0.020 moles per decimeter cubed potassium manganate 7 solution, KMnO4, and 14.30 centimeters cubed of the manganate 7 solution was needed to fully oxidize the iron 2 ions. Now the first question here, part A, is asking you to combine the half equations above to write an overall ionic equation. So remember, we have to have the same number of electrons in both half equations, so we times the bottom equation by 5, and then when we add them together, the electrons will cancel out. So it will be MnO4 plus 8H plus 5 Fe2 goes to Mn2 plus 4H2O plus 5 Fe3 . Now this overall equation will be very important to us when we attempt the calculation because it tells us the ratio of MnO4 to Fe2+. Now part B is asking you to calculate the number of moles of manganate 7 ions that react with the iron 2 ions. So to do this, we use the concentration of manganate 7, and that is 0.020, and we divide this by 1000 and we times it by the volume, which is 14.30. So if we do 0.020 divided by 1000 times 14.30, we get the moles of MnO4 and that will be equal to 2.86 times 10 to the minus 4. So here's question 1C and 1D. Once again, read through the question, pause the video, have a go at part C and D, and then we'll go through the answers. So part C is asking you to calculate the number of moles of Fe2+ present in the original 250 centimeter cube solution. Now in part B we worked out the moles of MnO4- that was needed to oxidize the iron 2 ions, and this was 2.86 times 10 to the minus 4. Now if we use the overall equation, we can see that there's a 1:5 ratio between MnO4 and Fe2+. So therefore, to work out the moles of Fe2+ in 25 centimeters cubed, which was the sample that we used in the titration, we just simply multiply the moles of MnO4 2.86 times 10 to the minus 4 by 5, and this comes out to be 1.43 times 10 to the minus 3. Now this is the moles of Fe2+ in 25 centimeters cubed, but remember the original sample was 250 centimeters cubed, because 25 centimeters cubed samples were removed from the 250 centimeters cubed original sample. So to work out the moles of Fe2+ in 250 centimeters cubed, I just simply times the moles of Fe2+ in 25 by 10, and this comes out to be 1.43 times 10 to the minus 2. Now part D is asking us to find the percentage of iron present in 4 grams of tablets. So to work out the mass of iron, we use the following equation. We use moles times the AR value of iron, which is 55.8. So therefore the mass of iron present in 250 centimeters cubed, the original solution, is 1.43 times 10 to the minus 2 times 55.8, and this gives us a mass of approximately 0.798 grams. Now that's the mass of iron in the 250 centimeters cube solution, but we want the percentage mass of iron in the tablets, and the tablets had a weight of 4 grams. So therefore the percentage mass of iron is 0.798 divided by 4 times 100, which gives us a percentage mass of iron of 19.95%. So here's a second practice question for you to have a go at. So read through the question, pause the video, have a go at it, and then we'll go for the answers. So this question says that 2.41 grams of a nail made from an alloy containing iron is dissolved in 100 centimeters cubed of acid, and the solution formed contains iron 2 ions, and 10 centimeters cubed portions of this solution are titrated with KMnO4, and the KMnO4 has a concentration of 0.02 and volume of 9.80 centimeters cubed is needed to react with the solution containing the iron. So the first thing we have to do here, if we're going to work out the percentage of iron by mass in the nail, is to work out the moles of manganate 7 that was needed to react with the iron 2+. So to do this, we use the following equation. It's concentration over 1,000 times volume, so therefore it would be 0.02 over 1,000 times 9.80, which will give us a number of moles of 1.96 times 10 to the minus 4. Now, once we know the moles of manganate 7, we can work out the moles of Fe2+ by just simply using the equation. So as manganate 7 and Fe2+ are in a 1:5 ratio, to work out the moles of Fe2+ in these 10 centimeters cubed samples, because that's what was used in the titration, we simply times the number of moles of manganate 7, 1.96 times 10 to the minus 4, by 5. And this gives us a number of moles equal to 9.80 times 10 to the minus 4. Now, we need to find the percentage of iron by mass in the nail. Now, the iron was dissolved in 100 centimeters cubed of acid, and samples of this were taken out 10 centimeters cubed at a time as part of the titration. So to find the moles of Fe2+ in the original solution, 100 centimeters cubed, we need to take the value that we've got for the moles of Fe2+ in 10 centimeters cubed and times it by 10, because there are 10 centimeter cubed samples in 100 centimeters cubed. So it would be 9.80 times 10 to the minus 4 times 10, which would be equal to 9.80 times 10 to the minus 3. Now we next need to work out the mass of iron in the original 100 centimeters cubed sample. So to do this, we just times the value of moles by the AR value of iron, which is 55.8. So if we do 9.80 times 10 to the minus 3 and we times it by 55.8, we will get the mass of iron in the original 100 centimeters cubed sample in grams, and this comes out to be as follows: 0.547 grams. Now we know the mass of iron in our 100 centimeters cubed solution is 0.547, so we need to work out the percentage mass of iron that was present in the nail. So therefore it would be 0.547 divided by the mass of the nail, 2.41, times by 100, which comes out to be 22.6%. Now the actual value is 22.697%, so this should really be rounded up to 22.7%. So here's our final practice question. Once again, read for the question, pause the video, have a go at it, and then we'll go for the answer. Now this question says a sample of steel, 1.15 grams, was dissolved in concentrated sulfuric acid and the solution made up to 250 centimeters cubed in a volumetric flask. Now 25 centimeters cubed of the solution was pipetted into a conical flask and titrated against 0.010 mole per decimeter cubed potassium dichromate 6 solution. 23.65 centimeters cubed of the dichromate 6 solution was required to reach the endpoint. Calculate the percentage of iron in the sample of steel. So the first thing I need to do here is work out the moles of dichromate solution that was needed to react with the iron. Now I have the concentration of the dichromate and I have the volume of the dichromate. So if I know the concentration and the volume, to work out moles of the dichromate, I just use concentration over 1,000 times volume, and that will be 0.010 divided by 1,000 times by 23.65. Now that gives us a number of moles equal to 2.365 times 10 to the minus 4. Now once I know the moles of dichromate, I use the overall equation to calculate the moles of Fe2+. Now dichromate and Fe2+ are in a 1:6 ratio. So therefore, to work out the moles of Fe2+ in 25 centimeters cubed, I just simply times the moles of dichromate by 6. So it's 2.365 times 10 to the minus 4 times 6, which is equal to 1.419 times 10 to the minus 3. Now once I've got the moles of Fe2+ in 25, I need to find the moles of Fe2+ in my original solution, which was 250 centimeters cubed. So I times the moles of Fe2+ in 25 by 10. And this is because 250 divided by 25 is 10. There are 10 lots of 25 in 250. So if I times it by 10, I get 1.419 times 10 to the minus 2. Now I'm trying to find out the percentage of iron in the sample of steel. So I now need to work out the mass of iron in my 250 centimeters cubed original solution. So I know the moles of Fe2+, which is 1.419 times 10 to the minus 2. I times it by the AR value of iron, which is 55.8, and that gives me the mass of iron in 250 centimeters cubed. So that comes out to be 0.792. Now to work out the percentage of iron in my sample of steel, I just go 0.792 divided by the mass of the steel, which is 1.15, and I times it by 100, and that gives me a percentage of 68.87%. So all these questions follow a similar pattern. First of all, you use the titration data to find the moles of the oxidizing agent that was needed in the reaction. Once you know the moles of the oxidizing agent, you can use the overall equation to work out the moles of Fe2+ in your conical flask. Once you know the moles of Fe2+ that was present in your conical flask, you can work out what the moles of Fe2+ was in the original solution. And once you know the moles of Fe2+ in your original solution, you can work out the mass of iron present and therefore the percentage of iron present. So that concludes this video lesson. So after watching this video, you should now be able to write iron-electron half equations for the reduction of common oxidizing agents such as MnO41- and Cr2O72- and be able to combine these with half equations representing oxidation of species such as iron 2. You should also be able to use data from Redox Titrations to find the concentration, mass and percentage mass of substances. So that concludes this video lesson. So please check out our YouTube channel, Dr. O Chemistry, which has lots of GCSE, AS and A-level videos, and our Twitter site @Radachemistry.